Okay, everyone. Nice to meet you once more this week. Welcome to the fourth edition, if I might say, of the African Women in Algebra Research Seminar. So today's speaker is someone I think we all know, the very famous Dr. Sarah Nakato. She's a dedicated pure mathematician, and she lectures at Kabbalah University. And she specializes in commutative algebra, factorization theory, integer valued polynomials, and cryptography. And she completed her PhD at Graz University of Technology in Austria in 2020. And she had served there as a researcher for 2 years. And she's not only passionate about teaching and research, but she actually also contributes as much of her time as possible, right, to mathematics initiatives in Africa, right? She's the co-founder and the current convener of Africa Women in Algebra. And today we'll be hearing from her on the topic of, we'll be hearing from her today, as I said. So she'll be talking about the ring of integer valued polynomials on the domain D. Yeah, and so I'll let her continue, right? So Sarah, the floor is yours.
Thank you, Nasrin, for the introduction. Good evening, everyone. Good afternoon. Thank you all for joining. So like the title says, I would like to share with you something on split integer valued polynomials. So this is joint work with Professor Sophie Frisch and Dr. Rosita Risner. So I will start with some preliminaries on integer valued polynomials, and then go and some factorization terms, then go to absolute irreducibility, and then I'll go straight away to the split, absolutely irreducibles. So we start with this ring of integer valued polynomials. So this ring, which we denote as int Z, consists of polynomials with coefficients from Q, such that when you input an integer, the output is an integer. So these are special elements of polynomials with coefficients from Q, such that when you input an integer, the output is an integer. So in particular, this is a subring of QX. So a quick example, Zx itself is an int Z. It's trivial in int Z because for any integer you pick, when you substitute in a polynomial with integer coefficients, what you get is an integer. The image is an integer. But you can have those outside Zx. For example, this polynomial has coefficients outside Z and it's integer valued. Because when you pick an even number, that will be even. When you substitute in F, that will be even. When you pick an odd number, that will be even. So any integer you pick, what you get, the image will be even up. So in other words, divisible by 2. So we get an integer for all integers. So the special thing about int Z is that you actually don't have to check on all integers. So it's known that a polynomial f in Qx is an int Z if f of a is in Z for all a's from 0 to the degree. So for int Z, there is a test set. So we don't have to check on all integers. You only check for images 0 up to the degree. And then once they are integers, you conclude that the given polynomial is integer valued. A quick example, I'm given this polynomial. So this is now not of that form that I can see, okay, for the evens, this can cater for the evens, that can cater for the odds, but I can use this criterion to check if it's an int Z. For example, when we feed in 0, so our degree in this case is 4. So when we feed in 0, we are going to get a 1, the image is 1. And then when we put in 1, we see that up we are going to get a 9 over 5, which is not an integer. And in that, we already conclude that this is not integer valued. In particular, this polynomial is not in int C because f of 1 is not an integer. So that's a very special thing about int z, that for it you don't have to worry about checking on all integers. There is a test set. So if I'm given such a polynomial in int z, still the degree is 2, I'll check images f of 0, f of 1, f of 2. And I already checked their integers, and I conclude that this is an integer valued polynomial. Another special thing about int z is that there are other number theory results that can give us elements of int z. For example, a product of n consecutive integers is divisible by n factorial. What does that mean? That if I have such a polynomial, it will be integer valued. Because any integer I will pick, I will get 3 consecutive integers up. And then that product has to be divisible by 6 or 3 factorial in particular. So this result gives us a very important type of elements in int z, which we call the binomial polynomials. That for each n, x choose n is in int z. These are n integers. So any integer we pick, we get n consecutive integers up, divisible by n factorial. So this is an int z. So what is special about binomial polynomials? So this form a z basis of int z as a z module. So in other words, I can write every integer valued polynomial as a z linear combination of binomial polynomials. And likewise, when I get a binomial polynomial and any integers, a z linear combination of binomial polynomials is always integer valued. Okay. Another result that gives us elements in int z is this polynomial. X to the power p minus x over p. This is an int z. This follows from Fermat's-Little theorem. That's why we are calling them Fermat's polynomials. So it follows from Fermat's-Little theorem that actually for all integers a to the power p is congruent to a mod p. So in particular, a to the power p minus a is divisible by p. So it gives us such polynomials. So one can pick any prime, maybe 19, I chose 19. So in this case, one does not even have to hustle, like finding images, F0, F1 up to F19. No, this result already tells us that this is integer valued. Great. So int z has generalizations. In particular, integer valued polynomials on arbitrary domains. So if D is a domain with quotient field K, the ring of integer value polynomials on D, which we denote by int D, consists of those polynomials with coefficients from K that map D to D. Likewise, when you input an element of D, the output is in D. And still, this is a subring of Kx. So these are polynomials with coefficients from K with this particular property. Great. But then unlike for the case of int z, where we have a test set that we don't have to check on all D, more generally for this general case, we don't have a test set. But for some domains D, there is a test set. For example, when D is a discrete valuation domain, so there is normal test set one can use. Or in other words, there have bases that have been brought in that line, along those lines. Okay. But what we can do is that for all f in kx, we can always write it as a g over b with g in dx and b non-zero. And such a polynomial in that form is an int d if and only if b divides the images gf for all a in D. The trivial example or the universal one, let's say, is dx. Dx is always contained in int D. Yeah. So this structure of integer valued polynomials is a friendly ring to deal with. For example, I mean, it's just a subring of kx. So we have, of course, there are several generalizations, but in this particular case, it's very easy to deal with. And it's known to provide examples and counter examples. For example, if you're looking for a non-Noetherian ring, a friendly ring that is non-Noetherian, look into int d. So whenever int d, so int d is always non-Noetherian whenever d is Noetherian and one-dimensional. So that gives us a bunch of domains where int d is non-Noetherian, because we have several domains that are Noetherian and one-dimensional. In particular, all the Dedekind domains satisfy that property. So a quick example is int z itself. int z is a friendly example of non-Noetherian rings. Great, but then for this talk, we are focusing on non-unique factorization. So we are focusing on the fact that int d in general is not a unique factorization domain. So in other words, it has non-unique factorizations of elements. A quick example. We have this polynomial. So this is integer valued because this is catering for the odd. For the even numbers, this is catering for the odds, such that this can split into those two irreducibles. So this is irreducible, like the example I gave at the beginning. This is catering for the even numbers. This is catering for the odd numbers. So it's irreducible, you can't split it. Whenever you try to split, what you get is not integer valued. And the same applies to this one. And these are two different factorizations of this particular element. More generally, together with Professor Frisch and Dr. Riesner, we proved that given any finite multiset of integers greater than 1, say 2, 2, 3, 5, there exists H in int D such that H factors into 2 irreducibles, other 2 irreducibles, other 3 irreducibles, and 5 irreducibles, and only those ones. So this is true for certain domains, the Dedekind domains with an additional property. In particular, it's true in int Z. So this shows that this structure of integer value polynomials has quite a wild factorization behavior. Like, for example, in this case. So this is true for any finite set. Whichever numbers you want, you can always get such a polynomial. Okay. So I've been talking about factorizations, irreducibles. Now let's define them very fast. Let R be commutative with identity. A non-zero element U in R is called a unit if there exists B in R such that UB is 1. So in other words, the units are the invertible elements. So for example, the units of Z are 1 and -1. And actually, these are the units of int Z. So more generally, the units of int D are exactly those units of D. Yes, so another definition is the irreducible. So a non-zero non-unit R is said to be irreducible in R if whenever R is AB, then either A or B is a unit. So in other words, we can't write R as a product of 2 non-units. So that's an irreducible element. A quick example are the prime numbers. So the primes, we know our prime numbers in Z, there's no way we can split it into 2 non-units or non-integers, non-unit integers or integers other than 1 and -1. Great, so a factorization, by a factorization, we mean an expression of an element as a product of irreducibles. So this is a factorization. Guess we are almost done with the factorization terms. We also need the length. The length of a factorization is the number of irreducible factors, n. So that's the length of a factorization. And then at times we have associated elements or associates. So we say that RS are associated in R if they differ by a unit. So in other words, there exists a unit U in R such that R is the product US. And we denote this by R is associated to S. For example, 5 and -5 are associates. Remember, the units in Z are 1 and -1. So 5 and -5 indeed differ by just a unit. Great. Now, finally, we have essentially the same and essentially different factorizations. That two factorizations of the same element, these two, are called essentially the same if they contain the same number of irreducibles, in other words, they're of the same length, and after a suitable reindexing, AJ is associated to BJ the other side. Otherwise, we call those factorizations essentially different. So in other words, in our non-unique factorizations, we consider some factorizations to be the same and others different. So it's what we are calling essentially the same and essentially different. A quick example. In this domain, we have 14 as 2 times 7, but it's also -2 times -7. So someone can say, yes, 14 is also -2 times -7. For us, these are essentially the same because 2 and -2 differ by a unit. Likewise, 7 and -7. So they differ by a unit. However, if I have 14 as 2 times 7 and this other factorization, these are clearly essentially different. So this is essentially different from that one. Okay. So that's essentially the same and essentially different. Now, taking you back a little to our theorem, so our factorizations were essentially different. But then one thing, in other words, this is essentially different from this, essentially different from that, and even this one. In any case, these are of different lengths, so they are clearly essentially different, but maybe these two. Yes, so one thing maybe I want to remark on this is our factorizations were square-free. In other words, we can't have G1 equal to G2, such that we have a G1 squared. And this is because of the existence of some irreducibles whose powers factor unexpectedly. So in other words, you have your G1 squared, you want it to be G1 times G1, but then it gives you another factorization. So that's the behavior looking at. Next is absolute irreducibility. That R is a commutative ring with identity. An irreducible element R in R is called absolutely irreducible if for all natural numbers n, every factorization of R to the power n is essentially the same as that. In other words, this is the expected behavior. You have your irreducible element, raise it to some power. You expect exactly those n copies. So for example, the prime elements normally behave in the expected way. So prime elements are absolutely irreducible. And in NC, it's known actually that for each n, remember the binomial polynomials I shared at the beginning, these are absolutely irreducible. So this is a recent result by Reisner and Vendish. Okay, so this is the expected behavior. Then the weird behavior or surprising behavior is now the non-absolutely irreducibles. That if R is irreducible, but there exists a natural number n greater than 1, such that R to the power n has other factorizations essentially different from the expected one, then R is called non-absolutely irreducible. So this is the surprising behavior. You have your irreducible element, raising it to a certain power, expecting only n copies of that power, of that element, but then it gives you another factorization. So those are the non-absolutely irreducible elements. So let's look at examples of this surprising behavior. In this particular ring, 3 is irreducible here. Z sits in there. So 3 is irreducible in there. And 3 squared is expected to give us 3 times 3. But then it also has another factorization. 3 squared is also 2 plus root minus 5 times 2 minus root minus 5. In that case, we say that 3 is a non-absolutely irreducible element of that ring. And more can happen, that in this ring, 3 to the power 4 should give us only 4 copies of 3 in the expected way, but then it also has another factorization. And in this case, it is moving from the length of 4 to even a length of 2. It's shrinking to a factorization of length 2. So more generally, such rings of integers of number fields will always have this behavior as long as they are non-unique factorization domains. So this is a result by Professor Chapman and Krause. So they showed that every irreducible element of any ring of integers of a number field K is absolutely irreducible if and only if OK is a unique factorization domain. That once I get such a ring of integers of a number field, and I find that it's not a unique factorization domain, I'm sure I will get such elements in there. Likewise, our integer valued polynomials have such elements. So let's look at that. So let's look at this element in int C. So this is in int C. Remember, at first we had some polynomial catering for the even numbers and another one for the odd numbers. In this case, we have 2 catering for the even numbers because of the square in the denominator. And then x squared plus 3 on its own caters for the even number, for the odd numbers. Such that once you square, you get the expected factorization, but then you can always do away with one of these because they are playing the same role. So once you square, you can just keep a squared here and then a squared the other side. And these 2 are different elements from this particular one. So we call this behavior interchangeability, that there are 2 polynomials playing the same role, such that when I raise to a power, I can always do away with the other. So I'll give a reference. They are general constructions of non-absolutely irreducible elements in int C. Okay, so now I guess we are ready for our split absolutely irreducibles. So our goal, we are given a discrete valuation domain, Rm, in short a DVR, with quotient field K and finite residue field. Our goal is to characterize such elements. So these are what we call the split polynomials. They split over K. So F is a product of those linear factor powers of these linear factors with the root set S. So S is a subring of R and M is a positive integers and C is a non-zero element of R. So this is a split polynomial and it splits over K. So our goal is to characterize polynomials of this form. And we need some definitions that are crucial in our characterization. One of them is a balance set. So what are these balance sets? Before we define them, we need a definition of an M-adic partition. So our Rm is still a DVR. S is a finite set. By an M-adic partition, C of R, we mean a finite partition of R into residue classes of powers of M. In particular, we are referring to such a C. So C is consisting of residue classes of powers of M, such that it's a so it covers R. Now that R is a union of these residue classes, and they are disjoint. These residue classes are disjoint. So we call such a C a partition, an M-adic partition of R. A quick example. Before the example, we have S, this S that gives us the M-adic partition, we call it a set of representatives of C, of this M-adic partition. Great, so a quick example is when we are in Z2, Z localize that 2, and we pick S as 0, 3. Then our C is, we can get other options, but we have 0 plus 2, and then also 3 plus 2. So these two are referring to Z2 and the other one also. Great, so this is an M-adic partition because these are disjoint, and they cover Z2. So in other words, the union of these two is Z2 and they are disjoint. So this is an M-adic partition. So now what's the balanced set? So we call S balanced if when we take for each S in S, the minimal n is such that this residue class contains no other elements of S than the resulting M-adic partitions that cover R. So what do we mean? It is such an S, but in this case, when we take each S and we keep this minimal, this resulting M-adic partitions cover R. So in other words, we require that NS is minimal in particular for that particular set S. A quick example is this itself. S itself is a balanced set. But maybe I'll give let's look at an example of how we really generate these balanced sets. Okay, so still we are in Z localize that 2. Our S is 0, 2, 3 is a balanced set. Now with partition 0 plus 4, that I do, and then 2 plus 4, and then 3 plus 2. So one thing we see that these are disjoint. They are disjoint and they cover R, but then I would like to show you how we generate this to bring it out very clearly. That to remember, Z localize that 2, we have the prime ideal there is 2 itself. So we have 2 levels. So we have mod 2 to the power 0. At that level, we have nothing. So at mod 2 to the power 1, we have 2 residue classes. We have 0 and 3 in this case. One could also choose 2. So in other words, once we have another class here, it already means that the intersection is not, those residue classes won't be disjoint. So for example, we can choose a 2, then 0 and that residue class, they won't be disjoint at this level. So that's why we move further to mod 2 to the power 2. Then at this point, we have 2 representatives, mod 4. 2 representatives of 2 mod 4, so that's why we have a 0 and a 2, and then for 3, we leave it like that. But if we wanted to continue, generate another balance set, we could continue down, and then here we could have maybe a 3 and maybe a 1. And then in that case, our balance set would be 0 plus 4, 2 plus 4, 3 plus 4, and then 1 plus 4, like that. So that's how we generate this balance set. Great, so with such a balance set, another definition we need is associating as a partition on a set. So we have a balance set, but not every set we pick will be a balance set. But then for every set, we can associate a partition, an M-adic partition that behaves like that of a balance set. And in reality, we are having like a balance set within that particular set S. So let's look at that partition. So an M-adic partition associated to a finite set. So we have S, a finite set. Then there exists a uniquely determined M-adic partition CS. Still, we have these residue classes, F, S plus M to the power NS, where S comes from now S. So such that every residue class S plus M to the power NS that occurs as a block of CS such so they contain both a residue class of M to the power NS plus 1 intersecting S and a residue class M to the power NS plus 1 disjoint from S. So that's a partition associated to a finite set. So you note that actually for any balanced set, this is true. For each of these residue classes, this is a union of a residue class mod M to the power NS plus 1 that is not disjoint from S, and then another one that is disjoint from S. I'll give an example. So such a partition is what we call a partition associated to S. So a quick example is already this, our partition that we had, CS, giving us 0 plus 4 and 2 plus 4, those cosets, and then 0 plus 4. So this is exactly 0 plus 8 union 4 plus 8. And similarly, 2 plus 4 is exactly 2 plus 8 union 4 plus 8. So we are increasing just by 1. So if this is true, we are having a partition such that each of these can be expressed as a union of one which is intersecting this S and then another disjoint from S. Then if this is true for any class here, then we call such a partition the partition associated to S. Okay. Now, with such a partition or with such a set, 0, 4, and so on, we call these which are disjoint from S. We call them the rich neighborhoods, and we call those that, no, we call these which intersect S, the rich neighborhoods, and those which are disjoint from S, the poor neighborhoods. So these are disjoint from S, these are not disjoint from S. So those are the definitions we're looking at next. So we have a finite set and a partition associated to it. An S-rich neighborhood is a residue class S plus M to the power NS plus 1 with S in S. So these are the ones which intersect S. And then the poor neighborhood still is a residue class of the form R plus M to the power NS plus 1 disjoint from S. So in particular, these are the rich neighborhoods, these are the poor neighborhoods. That's what we mean. And then the rich set of a set S is now the union of these rich neighborhoods. So that's the rich set, union of the rich neighborhoods. And then we also have the rich set of a polynomial. So if I have f in kx that splits over R, the rich set is exactly the rich set of its set of roots. So that's the rich set of a polynomial. So in our characterization, we want this rich set to be as small as possible. And we relate it to another set, which I should define next, the Porsche set. So what is this Porsche set? So the Porsche set of a polynomial f in kx, which we denote by pf, consists of those R in R such that the valuation of the images, of their images is greater than the minimum valuation over R. So in other words, the Porsche set consists of those elements in R that give us excess of what we want. So they give us more than the minimum valuation of all elements of R, in other words. And this is true for the rich set. Every element in the rich set also gives us more in the rich set. And then in the elements in the poor neighborhood, there are those which can give us more, and then there are those which give us, everything that give us minimum is in the poor neighborhood, but then there are those who can give us more. And then in our construction, we have it that the rich set should be exactly equal to the Porsche set. In other words, one thing I would like to remark is for any finite set S and G such a product with M, S, and N, The rich set is always contained in the posh set. So I think I already mentioned that everything in the rich set give us more. And everything, some elements in the poor neighborhood give us more, and everything that give us minimum is in the poor neighborhood. And then we want this posh set to be exactly equal to the rich set. So we have a way to handle that. And that leads us to the next definition, the partition matrix. So let S be a set of representative of the M-adic partition C. The partition matrix of C, which we denote by SC, consists of these entries AST, where now the diagonal entries are NS, when S is equal to T. The diagonal entries, in other words, we have NS, and then all the others are valuations S minus T. So in other words, it's a C by C or S by S matrix. So that's a partition matrix. A quick example is our partition. This, we had our set S, and we had a partition 0 plus 4, 2 plus 4, and 3 plus 2. Then we want the partition matrix. So in this case, our diagonal entries are exactly this. This is, we have a 2 to the power 2 in this particular end. And this is also a 2 to the power 2, and then a 2 to the power 1. And then these others are valuations of the difference. In other words, so this is 0 to 3, and then this is also 0 to 3. So the valuation in this case of 2 minus 0. And we are in Z localized that 2, we are referring exactly to the two-adic valuation. So that's how we get this one, and so on. So this other one will be the two-adic valuation of 3 minus 0, which is exactly 0, and so on. So this is how we get the partition matrix. Okay. Now we use this partition matrix to formulate a polynomial. So remember, I said we want a polynomial. We want the situation where the rich set is exactly equal to the posh set. And we construct that polynomial. So this matrix, so there is a lot of lemmas behind this. So this matrix is exactly catering for the poor neighborhoods. So this construction. Great. So we construct that polynomial that gives us exactly the rich set equal to the posh set, and that's what we call the equalizing polynomial of a balanced set. So our S is a balanced set, and A, the partition matrix of the partition associated to S. Then we define the equalizing polynomial of S as this product of those powers of linear factors with roots in S, where now this exponent, MS, these powers, is a uniquely determined unimodular solution over the positive integers to that system of equations. So we're now using our partition matrix. So unimodular, I mean the GCD of this MS must be 1. And then our X bar is XX, is what we are solving with S in S. So we solve this system of equations. And what we see as our E here is the minimum valuation over all elements of R. And that's what we want for like every poor neighborhood. Like we get exactly the minimum valuation. Great. So I've already said this, that actually when S is a balanced set and G the equalizing polynomial of S, then the rich set is exactly equal to the posh set. The rich set is equal to the posh set. So let's look at an example of this maybe. So for our partition, we had this partition and we got this matrix, and then we are solving the system AX bar equal to E bar, where is now the same element. And then on solving, I already solved. X naught is X2 is equal to 1, and then X3 is 3. When we solve this, this is what we get, such that our equalizing polynomial will be X minus 0, our root, the exponent is 1, The second one will be x minus 2, the exponent is 1. And the next one will be x minus 3, the exponent is 3, or the power is 3 in this case. So now this will be our equalizing polynomial of that S, our given set, because you already saw this is balanced. Okay, so now we use this equalizing polynomial, the resulting polynomial G over 2 to the power E. We prove that actually this equalizing polynomial over 2 to the power E, like I said, there are several things in the background. We call this E a fixed divisor. I'll define that a bit later. Yeah, so the resulting polynomial G over 2 to the power E, which is that is absolutely irreducible. So this is true whenever we get an equalizing polynomial over 2 over, but in this case we are in 2, but it can be any DVR. So the DVR, we have just one prime element, and it's the prime element I'm referring to in this case. So in case it's P to the power that E, whatever we get is an absolutely irreducible element in that particular DVR, int DVR. In particular, we proved that when we have a finite set S and it's balanced, and then G is the equalizing polynomial of S, and C is the fixed divisor. Okay, so C is DG, which we define as GCD of the images GA with A and D. This is what we call the fixed divisor actually. Then F is equal to G over C, is absolutely irreducible in its R. So when we have an equalizing polynomial over its fixed divisor, what we get is always an absolutely irreducible element in int R, depending on the R we have, the DVR we have. In particular, it's a full characterization that if S is a finite set and for each S in S, MS is in N, and we let G to be the product of these powers of linear factors with root set S, and then we set our F to be G over C, then we prove that F is absolutely irreducible in its R if and only if S is balanced, G is the equalizing polynomial of S, and C is the generator of the fixed divisor of G. So C is the GCD of those images. So it's an if and only if that given an absolutely irreducible element, I'm certain, like that split, in other words, G must be the equalizing polynomial of the root set and C must be the fixed divisor. And likewise, when I'm given a balanced set S, and S must be balanced in any case, the set of roots. So if I'm given a set, a finite set which is balanced, and its equalizing polynomial and the generator, the resulting polynomial, G must be that if R is a DVR, the absolutely irreducible polynomials of int R of this form that split correspond bijectively to balanced sets. In particular, when we are given an absolutely irreducible polynomial F, we map F to its set of roots. So that set will be balanced. And likewise, when we are given a balanced set, we get the equalizing polynomial and see a generator of the fixed divisor of that equalizing polynomial. Then we map S to F, G over C. So that's the bijection. And that was our full characterization actually of that split absolutely irreducible integer value polynomials over discrete valuation domains. So I'll give some references. The first one is a general reference for integer valued polynomials. The second one is the general reference for non-unique factorizations. And then 3 is where we can find the wild factorization behavior of int C. And then 4 is where we can find the wild factorization behavior of int D for this particular Dedekind domains. And then number 5 is what I've shared. The work I've shared is from number 5 and a split absolutely irreducible integer value polynomials over discrete valuation domains. And then number 6 is where one can find the factorization that non-absolutely and absolutely irreducible elements in rings of integers of number fields. And number 7 has constructions of non-absolutely irreducible elements. And then finally, number 8 has the absolute irreducibility of the binomial polynomials. Like I said, the binomial polynomials are known to be absolutely irreducible. So one can get the result in this particular paper. Right, thank you.